Hello everyone. This video is being made as a part of an assignment given to computer science students at Bennett University. Now in this video I'll be talking about closure properties of context-free languages. This topic is from the course Automata Theory and Computability. Now the properties we are going to talk about in this video are union, concatenation, clean star, intersection, and complementation. Now without any further ado, let's move on to union. In unions, let's assume we have two context-free languages having context-free grammars. We are denoting each with the symbols L1, L2 and G1, G2 for the grammars. Notice that we have a full-length tuple for the grammars. I'll be explaining what each of it means. Phi denotes all the non-terminals. Sigma, on the other hand, denotes all the terminals. R is all the set of rules, and S is nothing but the start symbol. Now, for both the grammars G1 and G2, I've taken an example on the right side. What you can see is that S1 produces the non-terminal A, the terminal A, the non-terminal S1, the terminal B, or the non-terminal the terminal A and the terminal B. And what this means is that we are producing a string, or all the strings which have equal number of A's and B's, where A is always followed by B. Now, to prove the union, let's say L1 union L2 is equal to new language, and so since union is nothing but an OR operator, we are applying the operator on S1 and S2 start symbols, and so S produces S1 or S2 is a new production rule, and we can use this production rule to create the grammar for our new language, which is L1 has a grammar as V1 union V2 union the non-terminal S. Now what this means is that we are including all the non-terminals in both the language L1, the grammar G1 and G2, including our newly defined S, which is a non-terminal. Now both these grammars have different set of terminals, which are A, B and C, D. So we are applying a union on both the sets. Similarly, we are applying a union on both the production rules R1 and R2, but since we have defined a new production rule, S produces S1 or S2, we are also combining it to the rules, the set of rules. Now the start symbol has been changed from S1 or S2 to a capital S, only because capital S is now capable of producing the union of both L1 and L2. Now note that I have written V1 intersection V2 equals phi. This is due to the reason that V1 or V2 may consider some similar letters to denote the corresponding non-terminals. But in reality, when you apply a union on V1 or V2, on V1 and V2, there is a chance that it becomes a crazy equation. So to avoid that, we use this condition, and hence CFL is closed under union. Coming to concatenation, similar to union, we assume two CFLs with CFGs and denote them as same, but for now we define a new language L, which has L1.L2. The dot represents concatenation, which means both L1 and L2 are all combined directly. So to To note this, we have a new production rule, which is S produces S1, S2. Now the grammar can be same as union, but now we just have a difference in the production rule, which is R1 union, R2 union. The production rule S produces S1, S2. Now why we have used S1, S2 is due to concatenation, and in union, since union acts as an OR operator, we use the OR operation. Similar to union, we assume that V1 intersection V2 equals phi, and since we are able to generate a grammar for our new language, which is concatenation, our CFL is closed under concatenation too. Coming to clean star, assume a CFL with CFG, and similar to previous, we define an L1 and G1 having a 4-length tuple, and for simplicity I've taken S1 produces just a terminal A. Now for clean star, let's define what clean star is. Clean star is nothing but an operation on any symbol which either produces an epsilon or any number of times the same symbol produced one after the other. So we have defined the new production rule S produces epsilon first, or S and an S1. Now what the S1 does is that it produces all the possible elements of the language, while the previous S or pre-appended S takes care of the clean star approach. So S can theoretically be looped recursively and produce any number of S1s. So now a new grammar is nothing but V1 union S, sigma 1, R1 union, the production rule S produces epsilon or S, S1, and the start symbol, which is an S. So below is the example of the language produced epsilon, A, double A, triple A, and so on. And hence we are able to generate a grammar, and so CFL is closed under clean star. Now for intersection, the most common non-CFL we are taking as an example is an L equals a to the power n, b to the power n, c to the power n, where n is greater than or equals to 0. Assume two CFLs with CFGs and let L1 equals a to the power n, b to the power n, but c to the power n m. Just with a slight deviation, we take L2 equals a to the power m, b to the power n, c to the power n. And notice that in L1, a and b are dependent. It ensures that a and b are in the same number, but c is independent. Similarly, L2 has an independent a, but the number of b's and c's are dependent. Now, what if we combine the two rules, which is nothing but intersection, because intersection on two sets of elements takes out the element which is common to both the sets. So, in other words, we are producing our initial non-CFL language a to the power n, b to the power n, c to the power n, which is nothing but L1 intersection L2 equals our initial language L. And hence, the intersection of two context-free languages is producing a non-context-free language. CFL is not closed under intersection. For complementation, we first take the famous De Morgan's laws and we define this: A intersection B equals the complement of a complement union B complement. Let L1, L2 be two CFLs and assume that CFL is closed under complementation. But using the previously said De Morgan's law, the complement of the union of L1 complement and L2 complement is nothing but L1 intersection L2. So what we are finally saying is that two CFLs, which are L1 and L2, applied on some operations of union and complementation, are leading to L1 intersection L2. But previously we have said that L1 intersection L2 might lead to a non-context-free language. So we have reached a contradiction where complementation on context-free languages is leading to intersection, or is also leading to, or might lead to, a non-context-free language. So our assumption that CFL is closed under complementation is wrong. Therefore, CFL is not closed under complementation. Now this video is made as an assignment, but also I've kept in my mind that there are many other people who should get the concept of this subject. Thank you for watching the video. This is Jagan signing off. Thank you.